For labeling and methodology, this slide explains the process we use to prepare the dataset for our AI model. So the first one is supervised framework. We use a supervised learning approach. This means that every image in our dataset was given a correct label before training the model. The model learns the relationship between the image and its correct category, which helps improve classification accuracy. The second one is high resolution collection. We collected high quality and high resolution image to ensure that important details were visible. Features such as color change, texture differences, and small visual patterns are important for the AI model to distinguish between different conditions of the object. The third one is manual annotation. After collecting the image, we manually check and label them to ensure the label were correct. These manually verified labels serve as the ground truth, meaning they act as the correct answers that the model used during training and evaluation. Class and dataset size. This slide shows the class used in our dataset and the total number of images prepared for training the AI model. So the first one is dataset classes. We divided our dataset into 3 fruit categories, which is apple, orange, and mango. For each fruit, the image were further classified according to their condition, such as fresh, bad, and good. For apple, most images belong to the fresh category, while a smaller portion represent bad and good condition. For orange, similar to apple, the majority of images are fresh with fewer images in the bad category. And mango, most images belong to the bad category with some fresh image included. This percentage bar show the distribution of image within each category. The second one is dataset size. In total, our dataset contains 255 synthesized image. This was achieved by using 85 images for each fruit category, resulting in a balanced dataset. The third one is balanced category. Having an equal number of images for each fruit prevents the model from becoming biased toward one particular class. This helps improve fairness and classification performance. The fourth one is model stability. The dataset structure was designed to work effectively with machine learning frameworks and helps the model learn more consistently during training. And the last one is visual diversity. We included images with different colors, lighting conditions, angles, and appearances to ensure that the model can generalize well to real-world situation. Class and dataset size. This slide shows the class used in our dataset and the total number of images prepared for training the AI model. So the first one is dataset classes. We divided our dataset into 3 fruit categories, which is apple, orange, and mango. For each fruit, the images were further classified according to their condition, such as fresh, bad, and good. For apple, most images belong to the fresh category, while a smaller portion represent bad and good condition. For orange, similar to apple, the majority of images are fresh with fewer images in the bad category. And mango, most images belong to the bad category with some fresh image included. This percentage bar show the distribution of image within each category. The second one is dataset size. In total, our dataset contains 255 synthesized image. This was achieved by using 85 images for each fruit category, resulting in a balanced dataset. The third one is balanced category. Having an equal number of images for each fruit prevents the model from becoming biased toward one particular class. This helps improve fairness and classification performance. The fourth one is model stability. The dataset structure was designed to work effectively with machine learning frameworks and helps the model learn more consistently during training. And the last one is visual diversity. We included image with different colors, lighting conditions, angles, and appearances to ensure that the model can generalize well to real-world situations.
So what MobileNet V2 is? MobileNet V2 is a lightweight neural network designed to be efficient without sacrificing any accuracy. In this diagram, first, ImageNet dataset. The model didn't start from zero. It was pre-trained on 1.4 million images. Bottleneck or frozen layers. These layers are logged, meaning they already know how to accept pictures like shape, age, color, or texture. Third is a final dense layer. This is the only part we train on our fruit dataset, which is 255 images. So here are the 3 steps of how MobileNet V2 works in our project. Step 1. The model already learned from millions of images through ImageNet, so it already understands basic visual pictures like shapes and colors. Step 2. The system automatically looks the computational layers. This saves a lot of computation times because just layers don't need to be retrained. Step 3. Only the final layers are retrained using our 255 fruit images. This is where our part comes in. The model learns to detect texture and color change specific to our fruit dataset. We train our model 3 times with different hyperparameter settings to find the best combination. So, what is a hyperparameter is? The hyperparameter are the settings we configure before training begins. The 3 main ones we adjust epoch, batch size, and learning rate. So, epoch means how many times the model goes through the entire dataset. More cycle means more learning, but too many can cause overfitting. And batch size. Batch size is how many images the model looks at one time. We kept this at 16 samples across all run because of memory limitation in the browser-based environment. So third is a learning rate. Learning rate controls how fast the model updates itself. Too fast and it means the best solution, too slow and it takes too long. As you can see, we reduce the epoch and increase the learning rate across each run to observe how it affected the model's performance. By comparing these 3 runs, we were able to identify which settings produce the most accurate and stable result.
For the result comparison, we have 3 rounds of result comparison. The first one we got for the orange 98.2%, for the apple we got 93.5%, and for the mango we got 81.4%. For second round we got apple 87%, orange we got 11%, and mango we got 90%. And for the third round, which is the last one of result comparison, apple we got 95%, for the orange we got 65%, and for the mango we got 90%. For the result comparison, we have 3 result comparison as I mentioned. Run 1 is the best because it does well with all 3 classes at the time. None of the class is run 1 get a score below 81%. The result is show a pattern. The learning rate goes up like this: 0.0001, 0.01, then 0.01. The score for orange goes down like this: 98.2%, then 65%, then 11%. This means the learning rate is too high for the data we are using. It does not just make the model learn slowly, it actually stops the model from working properly with the orange data. if we want a model that we can really trust, we should use a setting run 1. This setting are 50 epoch, a batch size of 16 and a learning rate of 0.0001. Run 1 settings are the choice for a model that we can trust. There is class differentiation. For mango spoilage, with high sensitivity to spoil 8 states, 90% of the decay samples correctly identified as bad. The network excels at identifying several color transitions, losing and noticeable surface damage. Orange texture. Achieve 89% accuracy, distinct run texture detail and specific skin pigmentation levels were critical diagnostic parameters assisting the model in separating classes and tags. Apple challenge. Prove the most difficult class, 87% accuracy. Gradual circular decay cause feature overlap between fresh and spoiled states, complicated by lighting fluctuations during training. Last one, project synthesis. From prototype to industrial reality, minimal data dependency. It can achieve 98% accuracy on specific classes with only 85 image proof that companies don't need massive, expensive dataset to build functional inspection model. Hardware efficiency. Running via teachable machine and mobile net V2 demonstrate that real-time quality assurance can be deployed in standard, low-cost browser environment without dedicated server time. The bottom line, the Freshness checker successfully validates rapid AI prototyping. It offers a tangible, cost-effective blueprint for automated visual inspection to actively reduce commercial food waste. That's all.
Okay, my name is Nurzati Izati and today I will present about the convolutional divide, extreme versus intermediate state. So now let's look at the technical reason behind this performance difference across the fruit state, which we call the convolutional divide. Okay, the model that we call as a bad state advantage is a fully rotten fruit exhibit highly distinct visual attributes such as example, dark spot, heavily wrinkled skin, several bruising and clear discoloration. Okay, this symptom present a strong, unmistakable convolutional feature that are easy for our teachable machine network to recognize and resulting in excellent classification accuracy for decay items such as our mango that correctly identify as 90% of bad state. Okay, in contrast, classifying the intermediate or the medium freshness state is a major technical challenge. A slightly discolored apple or a mildly texture of orange force the model mathematical representation vector to sit close to both the fresh and bad state boundaries because of the middle state that share feature with both good and the bad fruit. It will complicate the boundary separation and cause a minor dip in precision. Okay, moving on to the next. Okay, next slide is error analysis environmental failure mode. Okay, to wrap up the discussion, let's look at our error analysis that reveal two primary environmental failure modes. First, we have the spherical geometry overlap because an apple and orange share an almost identical baseline spherical shape. Okay, the model cannot rely on geometry anchoring to tell them apart. It is forced to rely almost entirely on micro texture and surface ring details, leaving a zero margin for error. Okay, the second one is the confusion matrix highlighted lightning interference. Okay, on what we call as the spectral confusion. Okay, if trained and testing the light environment directly alter the model perception of a color. When the environmental factors shift, the model struggle to differentiate between the similar spectral signature, causing the occasional misclassification between the color gradient of an apple and mango class. So understanding this visual boundary allow us to better stabilize future real world rollout. Okay, that's all.
you.